Hello everyone, my name is Cheng Yuan from Ant Group. I'm here to present our paper, AntVoice Neural Speaker Embedding System for FFSVC 2020. AntVoice system is designed for the Interspeech 2020 far-field speaker verification competition. It addresses the challenges related to far-field speaker verification tasks with more practical values. There are 3 tasks in the competition: far-field text-dependent speaker verification from single microphone array, far-field text-independent speaker verification from single microphone array, and far-field text-dependent speaker verification from distributed microphone arrays. AntVoice system is designed for the first 2 tasks of this competition. There are 2 main challenges in this competition. First, far-field speaker verification. Enrollment in close-talking microphones while tested in far-field microphone arrays. And there are background noise, room reverberations, mismatch between recording channels, and other challenges in this competition. The input is resampled to 16,000 Hz. 80 dim log-mel filter banks, a 25 millisecond sliding window, a 10 millisecond hop step size, CMN with a 3-second sliding window, and then capsule CMVN within the whole utterance. Using energy-based VAD to remove silent frames. During training, chunks of 1 to 4.5 second long segments are randomly sampled to form a mini batch of L frames. L is between 100 and 256 for first task, and L is between 200 to 450 for the second task. We use weighted prediction error WPE algorithm to reduce signal reverberation. Data augmentation, we use pi room acoustic simulate the room impulse response generator, and each utterance generates 5 replicates from diverse microphone arrays. Reverberation, background noise, music, and babble are respectively mixed into training samples at random signal-noise ratio between 0 to 20 dB. We use background noise of testing utterance to perform enrollment augmented trial by trial. Traditional popular encoder networks are TDNN as shown on the right side. And in this work, we use 4 encoder networks. First 2 are eTDNN and FTDNN. We use exponential linear unit rather than ReLU compared to TDNN. And 2 other encoder networks are ResNet and SE-ResNet. Squeeze-and-Excitation to model cross-channel interaction in convolutional networks. It explicitly models inter-channel dependency. A joint loss function is used in this work. It has additive cosine margin softmax loss and equidistant triplet-based loss. Each acts as a regularizer to the other. More discriminative speaker embedding from enhanced intra-class similarity and increased inter-class variance. EDT loss, poor matched samples closer by adaptively constraining two samples of the same class to be equally distant from another one of a different class in the triplet. We follow a two-stage training in this work. The pre-training uses Cobra in OpenSLR. Fine-tuning for the first task use Huijia dataset and the first 30 utterances of training dataset. In the second task, we use the remaining training dataset, both with extra augmented audio utterances. Optimizer is RADAM. Learning rate is scheduled with the cyclical strategy, with two benefits: to allow rapid traversal of saddle point plateaus and to meet the optimal learning rate. We use cosine similarity as the scoring method. We first whitening on extracted embedding features, then perform length normalization and average them into the speaker embedding. We use 4 encoder networks, and their results are ensembled, a linear combination of scores from encoder networks with weights tuned on development dataset. The results is evaluated based on mean DCF and EER. AntVoice system shows better performance than the baseline, even with single ResNet or SE-ResNet. We received the third place in the far-field text-independent speaker verification from single microphone array task for the competition. ResNet and SE-ResNet roundly surpass TDN type networks by a large margin. 2D convolutional networks in both time and frequency axes is more effective than 1D convolution. SE-ResNet contributes much more to performance improvement in the first task because of its cross-channel correlation modeling capability on short utterance. Joint function is superior to cos AMS loss, as shown in the right-hand side. And finally, whitening is significant in performance improvement. Refer to the table shown at the bottom. Conclusions. We present AntVoice system for the first 2 tracks of far-field speaker verification from single microphone array in FFSVC 2020. We use neural speaker embedding from deep neural network-based encoder networks. It has more practical values. We use 4 encoder networks: ETDNN, FTDNN, 2D convolutional residual networks, ResNet, and 2D convolutional Squeeze-and-Excitation residual networks in the work. A joint loss function, additive cosine margin softmax loss, and equidistant triplet-based loss. Performance gains with more discriminative speaker embedding from enhanced intra-class similarity and increased inter-class variance. Speech enhancement and data augmentation improves data quality and diversity. Finally, AntVoice system outperforms the baseline in both tracks and achieved third place in the text-dependent verification task. Thank you for your attention. If you have any questions, please contact our main author, Wang Zhiming, at this email address. Thank you.